So I'll get started here really quick. I apologize in advance. We've got a lot of material to cover. I want to start just by noting that the sky is not falling, right? Contrary to what you're probably seeing in a couple of media reports, this is bad, but it's not, and I don't really know where to scale it, right? Bad, is it heartbleed bad? Is it WannaCry bad? Is it, where are we at here? Shell shock bad? I don't really have a good scale for that at this point. I'll say that, we think that there's definitely some exposure. We think there's some things that actions you can take. Definitely want to make sure that you understand the vulnerabilities walking away from here, because I'm sure that your management has questions, unless they're living under a rock. Overall, I hope to get some good education pieces out of this. But look, realistically, the media is going to sensationalize this stuff. We know that. That's what they do. There's actions that you can take to minimize exposure, particularly for these critical workloads. But I think if there's any message you take away from this, the sky is not falling, right? So as far as an agenda goes, what are we looking to do here? I want to talk about, first off, what is Meltdown? What is Spectre? These are two significantly different vulnerabilities, and they're related. In fact, the papers were released under the same embargo. Some of the folks involved are identical, but again, even though they're related, they are two distinctly different vulnerabilities that will require different mitigations. Exploitation scenarios, we'll talk a little bit about those. How are the vulnerabilities alike and different, and then mitigations, right? There is more to this, unfortunately, than just patch. And I have patch in quotation marks for a reason, and then I'll give you a couple of closing thoughts before we go. So look, Meltdown, if you're a processor geek, this has got to be the coolest thing to happen to you since forever, right? And I don't mean to, celebrate a vulnerability. I'm a geek when it comes down to it. I really enjoy this stuff, and hey, man, at the end of the day, this is truly one of the coolest things that's happened to us in the processor geek world in a long time. That said, the basics of this, Meltdown is going to allow attackers to read arbitrary physical memory. This includes kernel memory. And this is obviously a big deal because you can read it from any unprivileged user process. I want to be very clear that this is not a specific or a vulnerability specific to a piece of software. This actually has to do with how the processor works, and we'll talk about this a little bit. Basically, Meltdown is going to use out-of-order instruction execution. Right? So a lot of people think about the instructions that a processor is executing. They picture these all executing serially, right? One after the other. Instruction 1, then instruction 2, then instruction 3 and 4 and 5. And look, that's not the way processors execute, and it hasn't been for a long time. If you've taken architecture classes in the past, you know that there are basically pipelining and parallelization of instructions. And what's happening here effectively is that Meltdown is taking advantage of the fact that instructions are very often executed basically out of order here. And what they're going to do here is they're going to leak data out via a covert channel. Now, a lot of you in InfoSec are probably familiar with the idea of a covert channel in networking. Basically, a covert channel being some unintended data transmission route. Here, what you're seeing is a covert channel basically on the processor itself, and this is going to involve processor memory cache. Right? Now, Meltdown was patched. It's patched in Windows, it's patched in Linux, it's patched in Mac, it's patched in Android, and Android technically is Linux anyway. But there's a Kaiser / KPTI, we'll talk about that in a little bit, patch that ultimately patched this, right? So this should be mitigated if you're applying all of your patches immediately as they come out, because of course, who doesn't do that, right? Okay, never mind. So look, a kernel ASLR, right? So address space layout randomization. This matters a lot because in an exploitation scenario, we don't want basically our attackers to be able just to go find addresses wherever they happen to lie. This is just a bad plan. Linux has implemented ASLR by default in the kernel. Now, they've been implementing it by default in user space for a long time, but the kernel implementing it by default in the kernel since 4.12. Now, if you're following along at home and you're like, where is that? That's pretty recent, right? So I'd say relatively recent. So if you've got an old CentOS 5 box, you probably don't have that. If you've got, deity forbid, Red Hat Enterprise Linux 3, like we see occasionally, you definitely don't have that. You get the idea here, right? So look, these out-of-support operating systems, haven't had this enabled by default. You probably don't have that enabled. This is something that you're going to want to apply patches for to enable. That said, kernel ASLR by itself doesn't fix this, but we do want to talk about some of the pieces around here. If we're going to go leak memory out of the kernel, we have to know where that memory is at, and that's because the 64-bit address space is just huge. In theory, you've got a 16 exabyte limit of memory. Realistically, because of the way processors are wired today, you really have 256 terabytes. Still, I don't want to read 256 terabytes of memory to go dump secrets from the kernel. The good news for attackers, bad news for us, randomization is limited to only 40 bits, meaning that locating the kernel offsets is relatively easy. You don't have to go check all of those. You basically have to go and walk your way through and step in and say, okay, inside of this piece of that address space, is there something? Nope. Okay, move on to the next one. So we're not brute forcing through. An attacker won't brute force through 256 terabytes of data. In practicality, you're looking at the paper they mentioned with an 8 gigabyte machine with 8 gigabytes of memory. They needed 128 guesses. Right? So not 128 terabytes, 128 guesses to get into kernel ASLR. So basically, the point here is that you can still get around, and people thought originally that this bug might only be useful to leak the address of something in kernel memory. We now know that it is very useful for leaking data from kernel memory, as well as physical memory in general. So we get into kernel ASLR. Look, Windows in general isn't much different in that not all the kernel is randomized. And this is a performance, basically a performance issue. Because the way the Windows memory manager is implemented, it's unlikely that you could get the entire physical memory out of the kernel. That doesn't mean that you should not worry if you're on Windows. Realistically, this could still be used to dump huge sections of the kernel. You just couldn't get a full physical memory dump. In Linux and Mac OS X, it is probable that you can dump the entirety of physical memory. Right. So and anybody who's done any memory forensics before knows how damning this is. But the reality is that on Windows, there's some people saying, I've seen some Twitter posts saying, well, don't worry, you can't dump all of physical memory on Windows. And I'm like, but who knows? 90%, I'm good with that. Right? That's more than enough for us to do privilege escalation and take over the system. So we have to talk about, to understand how this works or understand why this is a big deal and how these patches work, the page tables. Right? So our page tables contain the mappings between our virtual memory and our physical memory. And basically what's happening here is that your processes all use virtual memory. Your memory manager, the OS memory manager and the MMU, use this physical memory. And for performance reasons, these operating systems, modern operating systems, map kernel addresses into user space processes. Now, when people first hear this, when I'm teaching architecture and vulnerability development, exploit development, memory forensics, some people think this is a vulnerability. It in fact is not. Normally, if the processor is working the way it's intended, is not a vulnerability, because under normal circumstances, user processes can't read kernel memory. There's a descriptor privilege level, or a DPL, that's maintained, that basically if the DPL for the process, you may have heard about ring 3 and ring 0, right? Kernel memory being ring 0, user memory being ring 3. If you're in a user space process and you try to read kernel space memory, this triggers an exception, right? So if you don't have an exception handler in place, ultimately the process just crashes and dies, right? This is where we have to get into Meltdown, though, because remember, even though you can't access those memory addresses in kernel memory, understand that, at least without triggering an exception, understand that they're still mapped into the page table. So the user space process, in the way that the memory manager sees it, as this is swapped in, it's actually swapped in on a register called CR3, if anybody cares about that. But basically, your user space processes still can see kernel memory. They're just not allowed to see it, right? So picture that it's behind the wall, right? There's a wall between user space and kernel space memory there. There's a wall. They just can't see past the wall. So what's happening here? In a Meltdown attack, the attacker is going to launch a process, right? So that's what we've got laid out here with user space and kernel space memory. And inside that process, the attacker, non-privileged process, the attacker is going to create a large user space array. Now notice over here in the right, we see that the CPU cache has been cleared. There's also, as we look at here effectively, we've mapped this user space array, and this user process basically is going to go read a byte of arbitrary kernel memory. Now this is going to cause an exception, right? But here's the key, right? Basically, this read is constructed in a way that we are hoping what's the right word I'm looking for here? I guess constructing the code such that the read will happen out of order, right? And so as this read happens out of order, basically what's happening here is that it's going to read that byte, and then we're going to go write that byte to a piece of the user space array. And I'll talk about this in just a second. The idea here, though, is to get that side channel, basically that side channel leak performed. All right, so in step 2, we see the value of the secret data, right? So 1 byte at a time of secret data is ultimately used to populate an array that's readable in user space memory. Okay. Now again, I have to bear in mind here that there's a lot of moving parts to this. Initially, this read happens, but what's important to know is that due to out-of-order instruction processing, this user space array, you could argue that it briefly contains the secret data. It doesn't really matter to us at the end of the day because the exception fires, effectively the CPU, we'll talk about this a little bit later, the CPU effectively is snapshotting these operations when it does these out-of-order instructions, because some of these instructions might not be executed, like in the case of an exception. So even though the secret data is written here, we can never actually access it in the user space array. So again, by design, it's there, but again, it gets flushed back out, right? That checkpoint or snapshot gets reset before, basically before there's an issue. Okay, so what do we look at? What do we look at here? So we see the array offset basically here. Since we've written this into the array, what happens in the cache is that only that entry in the array gets flushed into gets pushed into the CPU cache. All right, so that's step 2. Step 3, basically exceptions trigger these out-of-order instructions, can't be read. Again, secret data is never accessible there. Basically, it gets rolled back, and we're set. But then we come into step 4, which somehow got labeled as step 5 up here, but I'll fix that before this goes to press. Anyway, step 4, the final step here, basically, is the unprivileged process is going to go iterate through its array elements. And I've kind of got some pseudocode here. Basically, what it's looking for is which array element has the minimum time for read. So they're going to read through, and basically with this array, what they've done is they've set up, or what you'll do is you'll set up an array of size 256, right? All the possible byte values. And you're going to go iterate from 0 to 255. And for each one of those reads, you're going to see which read happens the fastest. The read that happens the fastest is the one that was cached. Okay? And so the idea here is that by getting the cache or hitting the cache and basically flushing the cache between each read, because you see here 0x0 is slow, 1 is slow, 2 is slow, etc. 31, 0x31 fast, that's the cache hit. Right? All the other ones are referred to as cache misses. Okay? So when we see this cache hit, we're able then to infer or deduce, as it were, that 0x31 is the first byte of that secret data. What do we do then? We basically rinse, lather, repeat, and we leak another byte from memory. We're going to flush our CPU cache. We're going to go return to step 1, flush the CPU cache, read another byte of secret data, cause a cache hit in the CPU cache, and do it all over again. How fast can you do this? It actually depends on the architecture. All right, so there's some benchmarks in the paper that was released by Google and others that talk about ranging, depending on whether particular instructions are available, between 100 and 500K per second. Right, so non-negligible. This is not something where you're going to see go hit the cache and you're going to leak 1 byte every 3 minutes. But no, that's not it. We're talking 100 to 500K a second. So this is definitely the kind of thing that can very quickly trigger into a privilege escalation scenario. Okay, so the Linux developers, as you've probably heard about, have kernel page table isolation, or the Kaiser patch. You may have heard of this as. There's also a non-politically correct name that they were spinning around a little bit. I'm sure you can go look that up later. I find that humorous myself, but not SANS or business friendly, so I didn't put in the slides here. But the KPTI, kernel page table isolation, removes the mapping of kernel memory from user space processes. And the idea here is that with kernel memory no longer being accessible from a user space process, none of this matters, right? Because if we come back here, and again, if this secret data in the kernel isn't mapped into the user space process, this no longer matters, right? Now, I want to be very clear that this doesn't stop the vulnerability, right? All this changes. The only thing that this changes, right? The only thing that changes at all, actually, is the fact that basically that the secret data can no longer be leaked from the kernel, right? We could conceivably see other scenarios, although I have a hard time understanding how those scenarios would come about. I say a hard time understanding. I have a hard time picturing why this is useful to run your own process and leak data out of your own process. Maybe somebody figures out a way to exploit this later with a just-in-time compilation, maybe a Java, Python, JavaScript, etc., that then allows them to, to go dump memory in a way that, from the user space side, in a way that we hadn't previously thought about. I don't know that today. I'm sure that lots of really smart, really evil people are working on that right now. So look, because the kernel memory is no longer mapped, it can't be read by Meltdown. It's important to know that as you apply this patch, you will receive a non-negligible performance impact. I saw some numbers yesterday from Postgres, the SQL distribution, and they said somewhere in the 13 to 15%. I saw some other numbers today that said around 7%. So let's go with non-negligible. I don't think we know. I think it's heavily load dependent. Right? Obviously, the heavier load your servers are under, the bigger deal this is going to be. Right? But ultimately, there's a reason that we decided, or operating system developers decided to do this back in the day, to map those kernel addresses. It's for performance. So look, another problem that we're going to run into here, and I hate to be the bearer of bad news, is that some kernel memory, for instance, interrupt handlers, have to continue to be mapped into user space processes. There's no way around it. Right? So as these are mapped into user space processes, that's great. The question is, what can they do with these, right? Because a lot of future research, and in fact, they mentioned this in the paper, and I think this is going to be an area where we'll see some vulnerabilities. Future research is going to involve determining if leaking these small remnants of kernel memory can be used to dump other offsets in kernel memory. Because bear in mind, the patch doesn't stop the arbitrary read scenario. All the patch does is removes those addresses from being available in the process to be read. Right? So because we still see some of these page fault handlers and other interrupt handlers mapped into user space processes, I think it's realistic that someone will figure out a way. They talk a little bit about mitigation and counter mitigation in the very, very dense paper, dense academic paper. But look, realistically, I think a lot of that future research is going to be revolve around how can we take control of that, basically, of the system via that little kernel memory that's still there, right? Cannot emphatically enough address. This patch does not address the core vulnerability. It just prevents practical exploitation of that vulnerability. Right, so the practical exploit scenarios that have been considered today are and I'll talk more about this in a little bit, but really your multi-tenant environments. This is where you got a bunch of people to shell on a system, and only a couple of people with privileged access on the system, and only a couple of super users. And then basically what you're seeing then is the ability for one of those non-super users to become super user. Obviously, we don't want that. There was a rumor earlier that this was like an Intel-only problem, right? And where did that come from? Because I know there's a grain of truth in every rumor, and I like to get to that grain of truth pretty quickly. And it turns out this involves an instruction set called TSX. TSX allows for what they call transactional memory operations. And these transactional memory operations basically allow you to group instructions together for all or nothing execution, right? So this effectively, it's like a database, right? If you think about like a database transaction, for instance, you wouldn't allow a check to clear. You wouldn't check the balance and then authorize the check in two separate transactions because you'd have a race condition. Kind of the same thing going on here. And it turns out that for these Intel processors that support this, and these are relatively new processors that support it, but basically for the processors that support this allows faster exploitation because they don't need the software exception handling routine. And I think that they said with this, they could get around 500 kilobytes per second that they were able to leak out of memory, kernel memory, and with the basically with exception handlers, with software exception handlers, they were able to do it with 100K. So it really comes down to, does it really matter whether it's TSX or not? I don't know that I really care about it. 100 or 500K a second, it just doesn't matter to me. So what, it takes 5 times longer to leak the same amount of data. Vulnerability is vulnerability. Look, are ARM and AMD processors impacted? I think the short answer is maybe. The authors of the paper, the original research, didn't find practical exploitation scenarios on ARM or AMD. Remember that we're talking about out-of-order instructions, right? So basically the execution of out-of-order instructions caused this problem. It turns out that AMD and ARM both support out-of-order instructions. So they confirmed that in their research. They built some programs. They were able to view the fact that those programs were indeed executing instructions out of order. And they note that, hey, this may have something to do with optimization, right? Because remember, in a lot of these cases, or in every case, you need to flush the cache, and then you have to look at individual cache hits to be able to determine what was leaked out of memory. So again, this may be a spot for future research. It will not surprise me to find AMD processors, being vulnerable. So we're, I would say stand by on this, but at the moment, we don't have practical exploitation scenarios around ARM and AMD. Okay, so that's Meltdown. That's the first of the two, right? And earlier I said Meltdown was like the coolest thing that happened to CPU geeks, and I have to say this is actually a little cooler. It's a little less dense, actually, as it turns out, but it is actually a little bit cooler, and largely unpatched. So the basics. Look, Spectre abuses, instead of doing out-of-order instructions, it does something called branch prediction, as well as speculative execution. And again, same deal. They're going to leak data via some processor covert channel cache lines, effectively. Now, same thing that we talked about earlier. Cache line is your processor cache, and bear in mind there's a lot of oversimplification here. But the Intel processor manuals are like thousands of pages long, and we don't have time for that. So look, Spectre can only read memory from the current process, not the kernel, not other physical memory, not just the current process. Right, so I want you to understand, and I've got a great crosswalk at the end here. It's a good like one slide takeaway from this. But again, as you're trying to separate these two in your head, Spectre is only the current process. Meltdown is all physical memory. Right. So Spectre is being patched. I said doesn't appear to be patched. Is being patched. There are some basically what they're doing here. We'll talk about this in a little bit. Is basically they're flushing what they call the branch prediction cache. And this can cause problems with other stuff. We'll talk about that in a minute too. So look, speculative execution, what does this even mean? Our modern processors basically are executing ahead, right? This allows them to do parallelization as well as basically gaining lots of great performance here. The problem is when they execute ahead, sometimes they're going to reach branching instructions, if-else statements, for instance, right? So if A, then B kind of thing. Well, the problem is there's often an else. And what if condition A isn't satisfied? Should we still execute? Should they still speculatively execute? Well, the answer is, yeah, they do, but they do a CPU snapshot, basically. And when they do the CPU snapshot, this allows them to roll back in case you don't actually take the branch, right? So that's speculative execution. How do they know which branch to take? And it turns out that the answer to that is branch prediction. And for a long time, folks have been working with these branch prediction algorithms. And basically today, these are trained on the current execution of the process. And so as the process is executing, what's effectively happening is they're building up a database, I guess a database is probably the right word, of execution points, and noticing when we hit this branch, we jump here. When we execute this branch, we jump here. When we execute this branch, we jump here. And the idea is for that jump, and if you've ever taken exploitation courses, you know about return-oriented programming, or ROP. And basically, ROP allows you to go execute some code that's already in memory, right? So basically, you're borrowing code from a DLL that's already loaded. It turns out that Spectre does quite a bit of this, and it does branch prediction, or finds a branch prediction spot that hopefully jumps to the value in a register. Right? And the reason for that is it's basically saying, okay, now go jump here, now go jump here, and what it's doing then effectively is later replacing the value in that register to say, now go jump here. And when it goes and jumps here, it jumps to a new gadget that basically is invalidating or creating a cache hit, much like we saw with Meltdown. But over time, the CPU learns and I have quotes there because the CPU's not really learning, but from the training data, the CPU is understanding which branch to go execute because of previous executions in the same code. Now look, the Spectre vulnerability does not allow an unprivileged process to reprivilege memory. So I can't, from my attacker-controlled code in memory, I can't go access that secret data in the kernel. That's going to be blocked, right? It does allow code executing in the victim process to go access data it shouldn't have access to, right? So picture for a moment that you go to a web page and you get some JavaScript in your browser, and it turns out that Spectre actually came ready-made with not a weaponized proof of concept, but a JavaScript-built proof of concept so that you could basically use that, I say use that, or you could see, how this would be done in JavaScript. So it doesn't leave a lot to the imagination, right? That said, basically you're going to use that attacker control code to go try and read data out of the user space process. All right. So, again, in the case of Meltdown, picture you've got an attacker launching their own process on your system, right? And again, they would call it privilege escalation.exe or privilege escalation if you're on Linux, whatever. Basically, they would use that to go and privilege escalate on the system. Here, what you're dealing with is you've got an attacker who is able to introduce code. And again, I think browser is going to be the most likely scenario here, but I'm positive there are others. I can think about some Java RMI, remote method invocation. I'm thinking about some weird and honestly horribly written Python and Perl programs that basically take deserialized objects over a network. I call that a bad plan, whatever, but I picture those also being exploitable, although I would say in more limited scenarios, right? That said, again, it is fundamentally changing our threat model here. So look, Spectre, again, even if you've got that sandbox, that JavaScript sandbox, this allows it then to go read outside of that particular sandbox. And so, if we talk about how is it likely to be exploited, we think that, at least at this juncture, that it's going to allow the attacker to go escape the sandbox and leak data from elsewhere in the process. Where I see this being used most effectively is in basically a browser where you've got a tab containing attacker code and another tab running in the same process contains sensitive information that shouldn't be accessible to an attacker. If you put each tab in its own process, that would mitigate some of these types of attacks, but not all. And I'll talk about that in a couple of minutes as well. Okay, so get into exploit scenarios, right? We talked about how these work, and again, just to quickly hit and remind people, Meltdown is, again, largely privilege escalation. It's based on out-of-order instruction execution, whereas Spectre is probably most useful for leaking data out of a given process, probably not useful or as useful for privilege escalation, although I can see scenarios there too. And again, it's based on abusing the branch prediction and speculative execution algorithms. So Meltdown. I think there's two primary uses for Meltdown. Privilege escalation, and I think container like Docker and paravirtualization like Zen escapes, right? So let's talk about the first one, right? So privilege escalation. Any unpatched system, an attacker can execute a process, any privilege level. And my friends, even if you don't have multi-tenant environments, think very, very carefully about command injection on web servers, because this just took a new turn, right? And I'm not trying to be, hyperbolic or anything here. The arbitrary command execution, just became a bigger deal it's always been a big deal, don't get me wrong, but it became a bigger deal on an unpatched Linux server, unpatched any server, honestly. So basically here again, with physical memory, attackers can find password hashes or private keys, or if you can dump all the memory, you're dumping, you could conceivably dump the memory needed to perform a Mimikat style attack on Windows, right? There's been a couple of mentions, and leading up to the public disclosure yesterday, there was a lot of discussion about the fact that don't worry, this will only matter if you already have another vulnerability because of kernel address space layout randomization, or ASLR, right? That is not true. Yes, kernel ASLR is also bypassed, but I'm going to be straight up with you and just ask, who cares, right? I mean, yeah, if I've got a kernel exploit and I couldn't weaponize it because address spaces were randomized. Okay, cool. This allows me to now weaponize that because I'm unrandomizing the address space. But my friends, you don't need a kernel exploit if you can leak all the data, right? The thought was ahead of the embargo that potentially you could only leak an address. And if that were the case, if that truly were the case, you could only leak an address, then yes, this would only have been a KASLR bypass. We now know that's not the case, right? So KASLR is indeed bypassed, but your bigger concern at this point has to be privilege escalation. Second scenario that I have is container escape. Meltdown can target addresses that are shared between the container and host kernel in a number of different para-virtualization instances. So think about Zen, and then kernel sandboxes like Docker. Right? The ways that these achieve optimum memory usage is to share portions of the kernel between the guest and the host, or the root container and the child containers. It's possible that an attacker could leak data from outside the container, leading to a hypervisor escape. And let's not go with possible. Let's go with near certain, right? Because again, bear in mind that Docker is awesome, and I love Docker, and Zen is awesome, and I love Zen. But the reality is that, again, they're achieving basically these kernel segmentations in software. And remember that this is not a fault in software. This is a fault in hardware. Now, it turns out that when we talk about the patch, I mentioned here, is it being patched? Sure, KPTI is removing those kernel addresses from user space processes. That's a win, but it only matters because, right, again, it only matters here because there's a hardware vulnerability, right? So please separate in your head here that the patch is not addressing the core issue. The patch is making it harder to exploit the core issue, right? So again, container escape, we think is a realistic possibility here. Okay, so exploit scenarios. By the way, I'm going to come back around the container escape. At this time, I don't think that you can do this on VMware. I would say you can't do this on VMware, but I know better. Meaning, when I say I know better, I mean I know better than to make bold predictions like, no, you won't be able to do this. I'm going to say, I don't think you're going to be able to do this on VMware. I don't think you'll be able to do this on VirtualBox. But I'm cringing as I say this, right? Because I know it's going to come. I say I know. I feel like it could come back to bite me in the rear, right? Where I would be concerned, seriously, if you're using Docker as a security boundary, I would be really, really concerned. If you're using Zen, you probably got patches early, right? Commercial Zen, at least, you probably got patches early. Spectre. Let's talk about Spectre and the exploit scenarios here. My primary exploit scenario I see here is for JavaScript execution in the browser. I'm not going to say that you couldn't do this some other way. I mean, for instance, again, there's other JIT, just-in-time compile environments, with Java, JavaScript, Perl, Python, Ruby, insert scripting language here. I think that the scenarios for getting that code into the browser getting that code into that process are limited, right? So, like, for instance, I was thinking about macro code, but then I thought about, well, what do you do if I can get the user to execute macro code? Why do I care about Spectre, right? They're already pwned anyway, right? It's the escaping the JavaScript sandbox that matters to me. And that's really, we make a lot of assumptions in browser security about that sandbox being, basically being inviolable, and basically, that you can't break out of that sandbox. And this is going to, this does fundamentally break that assumption. Okay, so we see two probable uses for this: leaking data from browser memory, basically to get outside the JavaScript sandbox, and I'll talk about that in a second. And the second one is leaking addresses of user space modules to bypass ASLR. Now, I want to comment that this is, earlier I said with KASLR in good old Meltdown, I said I didn't really care about that. I do care about this. I care about this very much. So I am a little bit more worried about this one here because we've got a good history of browser bugs. Some of them have been patched. A lot of them have been patched. Some of them are, I'm sure, currently under embargo at any given time. And some people haven't applied those patches at any given time. And I know that looking at my web logs. My goodness, man, people patch your browsers, for goodness sake. But look, some browser vulnerabilities are very, very difficult to exploit because of ASLR. And this will fundamentally break that. It'll break ASLR, and it'll turn those impossible / very, very, very difficult to exploit vulnerabilities into trivial to exploit vulnerabilities. Okay, so leaking browser memory. Even if you've segmented even if each tab runs in its own process, or each browser window runs in its own process, I think the browser still contains lots of interesting stuff. You probably don't want other sites to be able to read this. We'll talk about a solution for this in Chrome as we close the session out. But look, I picture JavaScript maybe in a malvertisement, basically being sent down to leak browser cache and other saved data. My big worry, my number one worry, the thing that we're educating users on today, like user education on today, is, for the love of goodness, log out of your session. Don't just close the browser, log out of the session, because the difference here is that session key, when you log out, that session key is destroyed and it goes away. Right? If they log on with MFA, multi-factor authentication, and they're issued a valid token and they don't log out and they get hit, and that's in cache, that's in browser cache, it's in the process memory somewhere, right? And I won't lie to you and tell you I know how every browser works well enough to segment, or how it segments memory to. So my advice here, right off the bat, is make sure, for the love of goodness, you log out. Again, if you take one thing away from this today, right? One, the slide at the end with a nice crosswalk, and two, tell your users to log out of their sessions when they're done. Right? Huge, huge, huge win, right? So, I mean, good for security anyway, but as far as the why, it's because people are going to be exploiting this actively, I think, very quickly. So what about leaking module addresses? This scares me as well, but it scares me in a different way. A large number of these browser vulnerabilities, they're not practically exploitable, right? Meaning that we know how to get a crash, we don't know how to get exploitation, code execution, right? And so neat that you can crash a browser, but that doesn't give me anything as an attacker. It annoys you, but it doesn't give me anything. And so, ASLR and DEP, data execution prevention, they've limited browser exploitation, right? So first it was DEP, and then we knew how to get around DEP because, we would use return-oriented programming, ROP, and then ASLR came in, and we don't know where our gadgets are at in memory. Well, see, here's where the game changes, because Spectre allows us to go leak addresses out of memory, right? So when we can go leak those addresses of module and memory and bypass ASLR, we're taking a whole, and I don't think I'm overstating this here. I'm sure I'll have people that will argue with me on this too, but I think this is going to usher in a new age of practical browser exploitation until this is patched, right? Now, again, understanding that there are systems out there that we know are never going to be patched. I saw, I'll say this, every SANS class that I run, I have 2 or 3 students that bring a Mac that's, a non-Retina, it's an old Mac, right? And it's too old to have the latest operating system on it. And these folks are going to remain vulnerable to this forever. You can patch the browser, but remember, this, again, is a CPU problem, right? So Spectre and Meltdown both are CPU problems, right? Okay, so take that away, understand, of course, and Lance Spitzner actually runs the Securing the Human program, I think had a great tweet this morning. He said, hey, this is an example, these vulnerabilities more than anything else are an example of why you need up-to-date equipment, right? And I can't argue that. That said, you have the most current equipment in the world and still be Intel equipment in the world, you'd still be vulnerable to these. And by the way, again, I'm not picking on Intel. It just happens that the practical exploitation scenarios demonstrated have so far all been on Intel processors. Not to say that ARM and AMD aren't exploitable. I think that they are. I just don't have practical examples of that happening. Okay, so quick, Meltdown versus Spectre. If we talk about this as a cage match, this is 2 vulnerabilities enter, all your data leaves, right? Yeah, that's hyperbolic. But look, quickly here, in the, Meltdown versus Spectre, what do we see as far as, kind of a crosswalk here? And of course, these slides, again, will be made available immediately after the webcast. If you're following me on Twitter, I'm going to tweet out a link to a download for the slides. Otherwise, again, SANS will make them available later today too, I'm sure. But look, this is probably the one that you need if you're a management or want for a management. As far as Meltdown versus Spectre, you can see that Meltdown, again, summary of what we covered, allows kernel memory reads. It was patched by KPTI, or the Kaiser patch. The kernel page table isolation is what KPTI stands for. And then it does leak arbitrary user memory, right? Can Meltdown do that? Yes, although that's not the interesting part. The interesting part is leaking kernel memory. Spectre, of course, the interesting part is leaking arbitrary user memory. Could it be executed or exploited remotely? Meltdown, I can see some scenarios here where this happens, and the one that I'm thinking about particularly is coupling this with a command injection and going from an unprivileged web server command injection to full root access. All right, so that's when I say sometimes, and I'm sure there are other scenarios that we just haven't even. I can think about some complex systems that definitely are going to be vulnerable to this. I just again, with this being new and me thinking about vulnerability scenarios, I'll say sometimes. Spectre is a definitely, right? So now it's limited in what it can exploit, but can it be exploited and executed remotely? Yeah, definitely. This is going to be via JavaScript, right? As far as most likely to impact, I think kernel integrity is going to be your big one there, right? Privilege isolation, privilege execution, and as far as the Spectre, it's going to be browser memory. What do we have practical attacks against? The answer is for Meltdown, it's Intel, and for Spectre, we've got practical attacks. We think against Intel, AMD, and ARM, right? So kind of be aware of that. Kick that around a little bit. There's been a lot of people thinking about outside of the embargo, a lot of smart people thinking about how to limit limit the impact here, right? And we want to talk a little bit about that too, as far as the mitigations, right? So it is more than just patching, unfortunately. I know every time we come into one of these, we're like, patch now. Why, for the love of goodness, wouldn't you patch? Cool, neat, but realistically here, it's going to require more than a patch, right? Unfortunately, in Linux, KPTI has an obvious performance impact. We think it may be a little bit lower in Windows, but testing suggests less than 10%. I saw a couple numbers north of that, but let's say hovering around 10%. If you've got a server that is at 90-some-odd% utilization, or that regularly peaks out in utilization, you should absolutely consider the performance impact of patching, right? The worst thing you can do as a security professional is take a business unit offline. You all know that, or you wouldn't be here, right? But obviously, that's not a thing you want to do, and you could probably pretty easily do it. Patching on Windows may not actually patch if you're running third-party antivirus products. I wish I was joking about this. Man, do I wish I was joking. Unfortunately, I'm not. Kevin Beaumont has Gossy the Dog on Twitter. He has done an outstanding job this morning of putting together a list of antivirus patch statuses. Basically, as you apply the Windows patch, basically, and it's shared in a Google Sheet right now, and the Google Sheet URL is ridiculous. I know people don't like Bitly links. Suck it up, right? Or go search for it yourself. I don't know, but again, the Bitly link is there in an easy to follow format. Meltdown patch compat. Go take a look there and see where your antivirus company is at. Right, some of them are planning to release patches tomorrow. Some of them are evaluating the impact, et cetera. Right, so I don't want to pretend that this is not a small problem. It is. Most of your antivirus, all of your quality antivirus vendors, all of your mainstream ones, all run in the kernel. For performance reasons, they do some neat stuff that is likely to cause problems with, basically likely to cause problems when Windows changes the way the memory manager works. And that's fundamentally what they're doing here, is changing the way that their memory manager, their kernel memory manager works in order to patch these vulnerabilities. Symantec is known to cause blue screen of death. Right? So if you have Symantec, stand by. They publicly said that they expect to patch the AV engine tomorrow. But that said, today, if and again, I don't know how you feel about this. If you've got a multi-tenant environment, make a good risk decision about this, right? If you've got people running code, I'm thinking like terminal servers, right? If they're running code in your terminal servers and you use Symantec to protect that, I don't know what your plan is there, but at least have it in your risk evaluation, right? Take this from a, don't leave this in the unknown category, right? Basically, though, the way that this works is that when Microsoft patches the system, it sets looks for a registry key to determine whether or not to actually apply the patch. The patch is technically applied, but do they actually apply it in the kernel? They check for the registry key first. The third-party antiviruses have to actually go set that registry key. You, I'm sure, can now see the problem here, right? want you to consider systems that won't be patched. If you're not running any Windows Server 2003 or old Linux, hey, rock on, give yourself a pat on the back. You're doing awesome. For everybody else, for the rest of us, consider how these work. Take a look at the workload and understand that you now have, again, critical privilege escalation bugs that are highly unlikely to ever be patched. I don't picture Microsoft rolling this back to Server 2003. And man, do we have a lot of clients running Server 2003. I mean, in production workloads. They're not doing it because they hate security. They're doing it because they've got legacy code that works there and doesn't work elsewhere. Or they've got legacy code and the cost to upgrade is too high. This may change the calculus for some of them. I don't know. It's too early to tell. But again, put this in, add this to your risk decision. And great, you did a risk assessment last month. You've got to update. If you've ever talked to good risk assessors, they tell you risk assessment is a continuous process. As you get new information, you need to update that risk assessment. And I think this is definitely information worthy of updating your risk assessment. What about the cloud? I have mixed feelings about the cloud, and I always have, and I think I probably always will. All cloud hosting providers, public cloud hosting providers, patched the vulnerability before it was publicly known. So if you're on AWS, Amazon, Azure, et cetera, you should be good, right? If you're in a semi-private cloud provider instance, we work with a couple of managed service providers that run their own private clouds. I contacted 2 of them yesterday, and they did not know about the embargo, right? So, and because they're managed service providers, not managed security providers, we were actually tracking this for about a week prior to the release. We didn't know, obviously, the details, but we're tracking the fact that there have been changes, fundamental changes to Linux Memory Manager, the KPTI patches, and there were rumors kicking around, right? So basically, as we're talking to these folks, they're like, yeah, we'll patch when a patch comes out. I'm like, eek, right? But they weren't tracking this stuff at all. And I'm not saying go with AWS or Azure or whatever, but again, as you're thinking about risk decisions, and look, I love going with little guy. I really do. I find I get better service in a lot of cases. I'm not calling, I actually have somebody I can call, all that, right? But they didn't get the embargo information. And you probably have some private cloud instances, a lot of medical, firms or a lot of medical organizations that we work with, research hospitals, et cetera, have their own private cloud instances internally. They definitely didn't know about the embargo. And they're going to have to take outages to fix this, right? That's the reality. They're going to have to take outages. So when are they going to fix this? And in those multi-tenant environments, particularly for healthcare, if you happen to run a private cloud in healthcare, I would be very seriously looking at this because I'm not sure how lenient the Office of Civil Rights is going to be if one of your research users compromises data from another, and the deal, right? Browser memory isolation. I mentioned this a couple of minutes ago. Hacker Fantastic put this, basically put out a note last night about this. I read up on it, went in and enabled it because I can't see a reason not to do this. I want to be clear and say I don't think this is 100%. Meaning I don't think that this is a 100% fix, but I do like the fact that it causes Chrome to load each site into its own process. And we talked about the same origin policy. This is basically escaping that sandbox, right? Same origin policy is effectively a sandbox. I do think cache data is still in memory, right? So whether that's the encrypted variants of saved passwords, whether that's the some of your session keys for stuff you haven't logged out of, all that stuff. I think some of that's still in memory, but I do think that this site isolation is a good idea. I don't know, again, enough about the internals of Firefox or Edge to know for sure, do they have a comparable on this? Or, again, that stuff we'll be researching, I'm sure. And again, I think another great follow-up research point is how much of the browser cache data is still in memory anyway, even when this is, enabled. Okay. I want to talk about quickly too. This is not going to be the last hardware bug. If you download and read through the 16 pages of incredibly dense Spectre paper, they have a whole section on future work where they say, hey, here's some other stuff that we think is possible, but we didn't go after. as many academic papers do. They talk about their future work, and it's kind of planting a flag in the ground that if somebody else does the research later, they at least get credit for it as the thought leaders, I guess, as it were, right? I think that's important. I think multiple different researchers independently found these vulnerabilities while they were under embargo, right? So if you look at the papers, you will see that multiple different researchers found these. I think this is a fundamental shift in trust for the processor in general. And I think we need to look at architecting networks expecting more of these vulnerabilities to be discovered, right? For years, good security people, and I'm sure some of you in the audience fall into this category as well, have been telling clients and constituents, the CIO, et cetera, hey, different workloads of different sensitivity should not reside on the same physical server. I can't tell you how many times I've said that, how many times it's come out of my mouth. I step back and look at this, and consistently one of the questions I get is why? What's the worst that can happen? This is the worst that can happen. Okay, maybe it's not the worst that can happen. I don't know, but I'll say this is an exploitation scenario that is absolutely realistic, that is now in the wild, right? There's proof of concept code, easy to execute proof of concept code for Meltdown that'll beat kernel addresses, and multiple different people built it, within hours of this being public, right? Even the rumors were enough to get a couple of folks to build exploit code. Once they said, oh, I see the way the patch works in Linux. What could that be patching? Did some experimentation, started leaking kernel memory. Okay, so look, I want to give a couple of closing thoughts here, as we close this out. Look, I kind of hit this a second ago. I don't think this is the last one. We've known about attacks that impact microarchitecture CPUs. Stuff like these cache hits, cache misses. We've known about this for more than a decade. We thought in most cases they were only exploitable in very limited cases. Most of these we thought would involve physical access. Spectre and Meltdown attacks make it clear that these architecture decisions have to be rethought. Right? I mean, that's I think I'm probably preaching to the choir there. I'm sure there's a dumpster fire at Intel and AMD, and honestly anybody that makes processors right now, like saying, okay, even if you're not Intel, did we dodge a bullet? Where are we at? Et cetera. Right? What other attacks are coming down the pike? Because this is now an area of active research. And I think in the long term, you should expect to see more attacks on the CPU microarchitecture. I think the biggest impact here is going to be multi-tenant environments. All right. So as you architect your systems, I was mentioning how do you cross the streams there, or don't cross the streams, right? And again, I think it's a true wake-up call for those running workloads in shared environments, like the cloud. And again, whether you're in an environment that patched, whether you're in an environment that hasn't yet patched, obviously is going to change your risk model there. If you're in the cloud or have production workloads in a public cloud that's not AWS, it's not Azure, I think you need to step back and make a phone call quickly and say, have we patched? When are we patching? All that stuff, right? Particularly again for Meltdown. I'm going to close here and leave the slide up for a minute here. I think we may take a question or two, but before we do that, I want to quickly note that this was embargoed since believed to be June of last year, and that's a long time for this to be embargoed, and I have a hard time picturing that with all the email kicking around about this and closed kernel development mailing lists, that some nation states didn't know about and actively exploit this attack. Unfortunately, the indicators of compromise for this are, I'm going to go with near non-existent. I think in Spectre, might be a little bit easier. We might have some JavaScript being cached someplace or something. But look, for Meltdown, for privilege escalation, I don't think that I'm yet to see a good indicator of compromise that would tell me, yes, Meltdown was executed on the system. This is yet again a wake-up call to folks that are still in this we're going to keep the attackers out model. That's not the plan. It has to be minimized dwell time. All right. Again, I would say with medium to high confidence that nation states use this at least in some targeted attacks to escalate on systems that they had access to. But we're not yet root. That said, again, good monitoring of your systems, periodic threat hunting of your systems, and just good architecture decisions are going to future-proof you from attacks like these. I mentioned before at the start of the webcast, the sky is not falling.